So hello and welcome everybody. This is the first of the Open Mic Photonics series. As you know, we have this Open Mic event to provide you with a stage so that you can talk about your experiences, your feelings, maybe even your favorite paper that was published last week. So you can come here and talk to the B-Phot chapter's audience about it. So you could also be one of the next presenters for this event. We have a Google form that you can actually fill in with your idea and your information, and we'll get back to you. And you could also be in Spencer's chair for the next times. So for this session, we have Spencer, who's going to talk about photonics from big to small. We're going to see what that means in a bit. Just 2 pointers before I give the stage to Spencer. Firstly, keep your microphones off so that there is no interruptions. And secondly, please write down your questions in the chat box, or you can just write them down on a piece of paper and ask them in the Q&A session yourself. So with that, I give the stage to Spencer, please.
Okay, awesome. So yeah, first of all, nice to quote unquote meet you all. I came to B-Phot 1st of December of last year, so it's only been 3 months, and actually that kind of informs what I'm going to talk about. I call the talk photonics from big to small, but it's kind of mostly about the big because that's what I did in the past, and I've only been at B-Phot for a few months. Can you see my screen?
Yes, we can.
Great, perfect. So yeah, as I said, I've been at B-Phot for only 3 months. So the idea is to talk about what I did in the past, which was mostly really, really big things from a certain point of view. Also, their physical space, but also kind of the physics going on, and small, which is what I'm doing now. But I didn't want to talk about photonic integration and other topics that I'm working on now as if I was an expert on them, because I've only just started. So it's more going to be kind of the past looking forward. So just a little bit about what I'm doing now and more what I've done in the past, like during my PhD and postdoc. And in true open mic fashion, I did not practice the talk at all. So, you know, take that for what it's worth. About me, I've been around. I'm from the US. I was born in southern Indiana in Evansville here, but I grew up most of my childhood in the suburbs of Philadelphia, so the East Coast, until I was 18 or 17. And then I moved to Ann Arbor, Michigan to do my undergraduate at the University of Michigan. And I was there for 5 years. I took an extra year because I was playing Ultimate Frisbee at the time, and they had 5 years of eligibility, and I wanted to stay with my friends for an extra year. So I took one course in the whole last year. That's how much I wanted to stay there. And then after that, I moved to Texas, University of Texas in Austin. And the idea was actually to do a PhD, but during the second year I was there, or the end of the first year maybe, I met someone who's now my wife, and she's European. She moved back to Europe, and I decided to finish early and not do my PhD there. So I ended up finishing with a master's in Texas, and I moved to Europe. So I started my PhD at DESY in Hamburg. And after 3.5 years there, I got my PhD happily, and I moved to Paris to do a postdoc with my wife. Was there for almost 2 years. We got married, we had our son, and then at the end of 2019, I moved to Brussels. And then a year after that, I finally found a position in Brussels at VUB in B-Phot with Martin Wirt in his group, working on nonlinear laser dynamics. So that's kind of my trajectory very quickly. And yeah, that's where I am now. I'm a postdoc. I'm working on nonlinear laser dynamics, but I've been kind of all over the place. I also actually did an internship one summer in San Diego. Yeah, and that's kind of my history. I would tell you about what I did in Michigan and Texas, but I really feel like I became an actual scientist. Let's say I went from being a student to being a scientist while I was at DESY. And that was something that happened gradually, but I really feel like I can talk about the work that I did at DESY as something that I'm really proud was mine. The work I did at DESY was in the it's called LUX group, LUX group at the University of Hamburg, also at the Center for Free Electron Laser Science, and also at DESY. That's kind of a big campus there. It was in a big team, and it was a kind of project-based team, working with a very, very powerful laser, the Angus laser system, to try to do plasma acceleration, to then make undulator radiation. Sorry, I'm just seeing some messages in Teams. Let's see if they're from me. No, all good. And yeah, as I said, it was big. So the laser system took up an entire room, or let's say 2 rooms with a wall broken down in between. And it was producing 200 terawatts of peak power at a 5 hertz repetition rate. So it's a pulsed laser, 5 times per second, each pulse having, let's say, 5 joules of energy with a pulse duration of 25 femtoseconds. So it's really kind of an extreme photonics system. I mean, you even struggle to call it photonics at that point. And the experiment was happening downstairs. So the laser traveled 35 meters in a vacuum transport system to an experimental chamber where it was focused into a small plasma channel, usually of, let's say, nitrogen gas or some inert gas. And plasma acceleration would take place. And then we had a magnetic undulator to produce undulator radiation, which we did while I was there. And we published kind of our flagship result in 2020, where we did plasma acceleration 1 time per second in this case for more than 24 hours or 100,000 different shots, and showed that if we kind of train a model over some part, it can predict the output of that plasma accelerator, and you have to retrain it a few times during that time. But this was the big project-oriented thing that we did there, where I was, let's say, one member of a big team. I was mostly working on having the laser system operate reliably day to day. But I also had kind of a physics project in addition to that, where we collaborated with another team of Franz Kettner on the same campus to be part of his big project. This it's an ERC synergy grant that he and many other PIs had, called Axis, where they wanted to make an accelerator and a free electron laser, all based on laser and terahertz acceleration. Very complicated, ambitious project. And we, in the end, could help with one portion of it, where they wanted to use many cycle terahertz radiation to accelerate particles in a terahertz version of a linear accelerator. And basically, they weren't at the point where they could do this themselves. This was back in 2016. But we could use a side table in our laser lab to use our powerful laser to do some experiments related to that. And their goal was to try to get 1 millijoule of terahertz radiation, which for ultra short titanium sapphire laser isn't that much, but for terahertz, it's really a lot. And we ended up not surpassing that, but we got really close. What is terahertz again? It's basically electromagnetic waves with a certain frequency. And again, we're looking at pulsed terahertz sources. So there's 2 kind of different sources, very broad band in frequency, so like a single cycle, or more narrow band in frequency. These are different frequencies, so many cycles. And we were looking to generate something like this. And again, why we had to do it in our lab was because terahertz is actually rare. That's why it's interesting. There aren't a lot of laser materials that produce it. In nature, it's basically via low temperature black body emission. In the lab, it can come from charged particle interaction, or frequency mixing, but we wanted a really high energy, like strong beam. And the only way to really do that is with laser driven nonlinear optics. And we ended up using something called lithium niobate. It's a very popular Chi2 large Chi2 material that's being used in a lot of photonic integrated circuits. Actually, a group in Harvard is kind of pioneering that with a lot of other groups, obviously. And we did it this way. So we took our laser system, the laser system that takes up a whole room. We split it so that there were two copies of the pulses, completely overlapped in space and time, except with a time delay. And these are actually chirped pulses, so that it's before they're compressed to the femtosecond duration. So you can imagine they have different colors at different times. And then if you look at one slice, it's one frequency here and a slightly different frequency here. You put them through lithium niobate and you get out terahertz, basically. It's something called quasi-phase matching when it's in a periodically pulled device like this. And we saw that as you change this time delay, there's a peak in the efficiency, which is when the difference in frequencies here matches the periodicity here. And that was kind of the successful result. After, I guess, a year and a half or 2 years of really optimizing this in every way, doing simulations, trying a lot of different things, maybe damaging a few crystals, we got to this point. So this is kind of the most complex that we did. So we split the pulses. We modified their phase a little bit with chirped mirrors and high dispersion glass. We recombined them so each output of this interferometer is identical. We sent them into two identical crystals that are in vacuum chambers, cryogenically cooled, and we measured the output. So this was kind of the culmination of everything we did for those like 2.5 years. And the experiment looked really cool. I have a video of it too, but I just couldn't get it to play properly. This is the two different vacuum chambers, both down to 80 Kelvin at the same time, roughly. It's a cryo module here with a cryo finger, so a copper piece inside the vacuum chamber with the crystal mounted on the bottom. You can actually see the crystal in there. So the crystal is mounted on this copper piece, which is in thermal contact with the liquid nitrogen, but this is in vacuum, and we have windows here, and the laser is actually going, pew, 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 in each case. And in each case, it's two copies of the laser that have been shaped properly to maximize the efficiency, and each arm is exactly the same. And we measure the output of the terahertz in each case. And we actually use, this is polyethylene to block the laser light, and you can see that it's damaged there from blocking the near infrared laser light, and only the terahertz transmits through. And we measure with a detector. And this is the big 1 joule laser pulse that we're using to pump these nonlinear crystals. So it looks cool, and you use liquid nitrogen, which is always fun. And in the end, we got a peak output as we cranked up the laser system. We got a peak output. This is in each crystal, and it sums up to more than 600 microjoule or 0.6 millijoule. And basically, that was my PhD. I think I had at this point already written most of my thesis, if not all of it. We did some more experiments, and I was lucky enough to be able to add, replace one number with a higher number in the thesis and add a few figures with this kind of result. So that was super fun, and I finished the end of 2017, and I defended in early January of 2018, and then I moved to the CEA south of Paris. I lived in Paris, just on the bottom edge, to work with Fabien Quéré in a group called Physics at High Intensity. So it's again using big laser systems, a lot of plasma physics, particle acceleration again. But I was working here where it's intense laser metrology. So we didn't necessarily care about the pulses being high energy. They just needed to be ultra short. And they also had a big laser system. It's called UHI 100. So instead of 200 terawatts, it's 100 terawatt, but very, very similar system. Also taking up a room. They also had laser transport that went down into the basement, where they had actually two different experimental chambers for different reasons. But in the case of the CEA, I actually wasn't really working on the laser system anymore. I was just working on small experiments. So every once in a while, when there was some time, I would take my device and I would go into the experimental chamber and do some measurements. And I wasn't doing really high energy stuff anymore. I was always attenuating it, just worried about shaping the laser pulse. At the CEA, I changed topics. So I wasn't working on terahertz generation anymore or laser acceleration. I was working on something called spatiotemporal couplings. So it's an additional complexity. So besides the laser pulses being short, being a pulse laser in the first place and also being ultra short, we worried about an even more complex aberration, let's call them. So to try to explain it, if you have a CW laser pulse, it's really big. It doesn't have to be big, but it's just going, it's propagating. And you have the wavefront, which is how you describe the spatial phase. If everything is good, it's flat and it's just going to propagate. If it's curved, then that means it's converging, so it's going to go to a focus. If it's curved the opposite direction, it's going to diverge. And if it has some, let's say, waviness or asymmetry, it's going to propagate in maybe a way that you don't want to. For example, astigmatism, which is the same astigmatism you can have in your eye, is when the curvature is different in one axis. So like kind of like this, and then the other axis in and out of the page, it has a different curvature, which if you were to focus it or let it propagate a long way, you would go from like a round beam to an oval, something like that. That's kind of the first way to think about it. But then if you say, okay, it's not a CW continuous wave laser anymore, it's ultra short. So now it has a short pulse duration. It still has this wavefront that's described in a similar way, but it also has a pulse front, which is when the energy of the laser pulse arrives, onto your detector or whatever you have. And that makes it more complex. And this picture here is also kind of the perfect case where both are flat and also coincident. They're in the same place. You could have an arbitrary case where the wavefront has imperfections and wiggles on it, but so does the pulse front, and they're not actually coincident, so they're not the same anymore. And it turns out to be able to describe this in the equations for laser pulse and its propagation is very complicated. The easy way to describe it is that there are spatially dependent temporal properties, which is the same as saying there are temporally dependent spatial properties. And if you agree that there's a time frequency duality, so an ultra short pulse has a broad spectrum, then another way to describe this is that there are spatially dependent frequency aberrations. So the simplest way to look at this is that it's very strange chromatic properties of ultra short laser pulse. So if you imagine you're imaging with a camera, if you have the chromatic aberration, the different colors of your scene, a blue shirt and a green tree, are going to focus to different places on the camera, and you'll have a little bit of blurriness there. It'll limit how sharp you can focus or how small of an object you can see. But for an ultra short pulse, it will lead to your pulse looking like this. So strange. And a way to describe it, or let's say a way to visualize it, is one simple example, which is called pulse front tilt. And it's when a beam propagates through an angularly dispersive optical system. But it's basically a system where the different colors will, when they go through it, travel in different directions. And the most simple version is a prism, where the reason why this happens, so the pulse front and wavefront are coincident going in, and then when they're going out, they're no longer coincident. And the reason that happens is because the group velocity and the phase velocity are different inside this prism. So even if it's just made from glass, the simplest glass you can imagine, this is true because it's dispersive. So one wavelength will go in and it will refract at this surface and will go out at 5 degrees, and a different wavelength will go out at 8 degrees. And what this results in the pulse is that the pulse is traveling in one direction, but the energy in the pulse is actually arriving at different times at different positions in the pulse. And I'm describing this as if it's very exotic, but the papers that described it first are from the late 80s and early 90s. So it's a very, very well-known phenomenon, even for femtosecond pulses, which back then were were not super common in the lab. And another, let's say the next complex version of that is called pulse-front curvature, and it's the same exact phenomenon, but it's with a lens. So like a really thick single lens will make a ultra short pulse have a curvature of its pulse front relative to the phase front. And if you were using this lens to image a scene, like I described before, it would have chromatic aberration. So you wouldn't be able to image your scene as nicely as you would hope to, which is why a lot of lenses and cameras have many lenses actually. So what you consider your lens for your camera has many inside. One of those reasons is to eliminate the chromatic aberration. So if you're using a lens like that for your femtosecond pulse, you're going to get what's called pulse front curvature. And it happens a lot of times in a telescope. If you just want to make your beam go from small to big or from big to small, you think you can just use normal lenses, and it doesn't work. And again, this was described in 1989. So it's not news to anybody in the field, at least. But we, in addition to trying to measure these, that was one of my main tasks, was to try to make devices that could measure these, let's say, exotic phenomenon. We also studied more complex examples of these aberrations. And one of them eventually was called the flying focus, is light bursts that have controllable velocity in vacuum. So we're not proving, relativity right or wrong here. It's actually the speed of light doesn't change, but you can change the arrival time of different colors in an ultra short pulse with temporal chirp. And if you have them focusing to different positions, then you can basically control the arrival time of the intensity. So I'm going to play a video here. The top case is going to be normal, traveling at the speed of light. So it's the animation is going to step through time, and a laser pulse is going to fly through here at the speed of light. And these other three examples have spatiotemporal couplings on them. It's all simulated, it's not measured, that make them travel at a velocity different than the speed of light. So this is traveling at the speed of light. This one is traveling backwards. This one is traveling slower than the speed of light. And this one is actually accelerating. So this is a way to create a controllable velocity of the intensity of the laser light. So it's not the information. If you had information in there, if you want to look at it from that point of view, it's not traveling any faster or slower than the speed of light, but it is the intensity. So there are some applications where only the intensity matters. This was demonstrated experimentally. So Fabian, my boss, they published before I started the theoretical derivation. A group in Rochester kind of scooped us and published the experimental demonstration, and then I published a slightly different experimental demonstration in 2020. So that's one of the examples of something I was working with at the CEA. Okay, so fast forward to now. Now I'm at B-Phot, and I'm in the nonlinear dynamics team with Martin Wirt, with Robe and with Martin. Both, they're working on two different projects of Martin, and we have also Thomas and Nitish in this Fiona project, and there are also more people coming because of Martin's recent ERC, which probably most of you know about. So I'm part of this team, and let's say my main task right now is to learn about and to help and to contribute to the Hex Micro and Fiona projects and the PhDs of Robe and Martin. But the additional, let's say, challenge or opportunity is to try to do something together with Martin and at B-Phot. That's a merge of everything I just explained to you and the work that Martin is doing. So what does the future hold at B-Phot? Again, I've been here 3 months, so basically been completely working on these two projects and getting up to speed and helping Robe and Martin, and especially for these guidance committees. And kind of there's my past work, which I guess, I'm saying goodbye to, bye-bye. But there is a lot of potential for taking the expertise of these spatial temporal couplings, let's say, which is for me the most interesting part of my recent work, and seeing if I can make it match somehow. One example is looking at nonlinear dynamics and chaos in integrated lasers that are ultra short, which is that's my expertise, but everything else is intimately related to Martin's work and the work that Rob and Martin are doing, and seeing if there's some type of translation from spatial temporal couplings in free space, which I was showing before, and some type of multi-mode nature of integrated waveguides. So this is kind of like, let's say, experimental, experiential, unknown type of topic. And in addition to these ideas that I'm putting out there, I'm trying to find ways to leverage the overlapping experience that I have and people at B-Phot have. So, as I said in the beginning, I can't really say too much about what I'm doing now, in the sense that I've been doing it for 3 months, and my priority is basically getting up to speed and helping people as much as possible. And I trust that these ideas and synergies and expertise will just come out. And I've been working mostly with Martin, and Robe, but we'll see if anybody else at B-Phot kind of is inspired by what I presented today. That's the point of the open mic, I guess. So yeah, now I open to questions. So let's see, that was 24 minutes, so not too bad.
Yeah, that's actually great. Thank you so much for your presentation. It was amazing. I see Yousef has a question. So please, Yousef, you can.
Yes.
Yeah, I'm gonna quit. Yeah.
Okay. Very, very actually impressive, to be honest. The work that you've done in the past, also what you're planning to do here. I saw. I've actually 2 questions for you. Since it's an open mic, I'm gonna just be very naive in questioning. Okay, so I'm not gonna wash myself. All right.
Please don't. Yeah.
All right. First of all, just a crazy idea. You know a lot about nonlinear optics, given your experience, I would say. And the question is, have you seen anyone doing anything nonlinear in particular with water, like photo bleaching it selectively, or kind of sort of trying to get some stimulated emission from it without causing its structure to break down?
So with water, yeah. So I have seen some.
I mean H2O in liquid. Yeah. Okay, let's be clear on that. Not vaporized.
Yeah. So I spoke about terahertz generation, the stuff during my PhD, and obviously we were working on one very specific regime of that, and got really into how to make that specific case work. But there's a lot of different, let's say, schematics or regimes where you can generate terahertz. You can do it also when you ionize air. They use 2 colors, so they frequency double one and they overlap them. But a group, I think since 2018 or 2019, or maybe even earlier, started showing results where they generated terahertz from jets of water. So, which doesn't make sense, because they would make. I think they did it with like, a jet, so like a stream of water that's like, let's say a wire of water, but also 2-dimensional sheets, and they were focusing laser light onto that. But the question is, how does that work? Because water is supposed to be isotropic, so it's centrosymmetric. It doesn't have chi2. So how is this nonlinear process happening?
I don't think it's coming from the jet.
But I don't. Yeah. So I think, at least in the papers that I read, they showed the experimental results and made some justification, but the process, the real first principle process of why it was happening wasn't completely clear. So I think there are probably competing ideas on why it works. I've also seen people use terahertz radiation to measure the properties of water. So water should have some chi3, and it might be only non-zero in the terahertz range. I think there's a professor in Bochum in Germany who has an ERC grant that's related to measuring the properties of water with terahertz radiation.
Okay.
But I don't
Well,
know 100% if that's true.
I will check that waterjet paper. It's pretty interesting to know.
Yeah,
And I just had another question too.
Xicheng Zhang, who's at Rochester, but also at a Chinese university.
Oh, right. Well, that's interesting. I also had another question. At the end, you mentioned that on your current work on B-Phot, you mentioned, if I'm not wrong, femtosecond kind of short pulse lasers or ultra short pulse lasers in integrated photonics. Is that correct, or did I misread?
That is what I mentioned as a possible avenue,
Possible.
potential
Good.
future development.
Do you think that it's potentially possible to have a laser on chip that provides, well, enough, how do you call it, like enough intense and pulses in the wavelength regions of something like BCAR, something like broadband coherent anti-static Raman spectroscopy? It would be wavelengths, as I think, around 1100.
I mean, I think, the question usually is how high of an energy do you need? Because generally it can be possible.
Millijoules, basically.
Yeah, I would guess that's not possible, because normally on integrated circuits, you're looking at picojoule energy levels. So it's really a different regime. Usually you have on integrated circuits, because they're small cavity lengths, you have picojoule energies, but 10 or 20 or 40 gigahertz repetition rate. So it's a kind of a different part of the parameter space.
And what about resonating it? Do you think it could be an idea somehow, having a resonator to increase the intensity or just something pretty stupid, eh?
Yeah, I don't know.
Well, okay, thanks very much.
Someone raised their hand.
Yeah, it was me. Can I just comment here about getting like 1100 nanometers and stuff like that? Well, you can actually use nonlinearity by doping different kind of erbium molecules in the silica waveguide and using like high powers to generate with frequency comb, I think, or four-wave mixing, something like that, to generate some sufficient energy wavelengths, I guess. Can it be? I mean, it's something that nonlinearity is doing now in the integrated circuit. And yeah, it depends. Considering the size of chips, they are small and there is a heating issue, I think, Yousef, and getting like all this energy there is not only the problem of getting the laser on it, but also is the problem how to deal with that heating problems, because sometimes heat can really damage the structure more than can give you a sufficient amount of data, right? So there is always a trade-off, but nonlinearity can be used for four-wave mixing to get the different wavelengths and going to far infrared region also. And since I'm there, I just wanted to say how impressive was your path, Spencer, from US to Belgium.
Thank you. Thank you.
It's really impressive.
So thank you very much, but we shouldn't hide behind the CV or the publications or anything. I came to Belgium in December of 2019 with my wife and son, who then was only a few months old. And the idea was to I had written some proposals, and I was hoping to start in the middle of 2020, and all my proposals were rejected. So I was happy on one hand to hang out with my son for longer, but I didn't have things looking out. And actually, Martin at B-Phot offered me a job eventually, and I started in December. But if you asked me in July or August or September of last year how optimistic I was about the future, I probably wouldn't have given you a very optimistic answer. So you know,
Yeah, I
thank you,
understand.
but
Yeah.
you know, there's struggles.
But maybe you needed that time, in fact, just to get better possibility and get B-Phot. Who knows? It's the destiny, right?
We have to look at it that way.
Exactly.
There's no other way to look at it. Yeah.
Yeah. It's a good luck here. Good luck in B-Phot, and hopefully very soon we can meet again in person. I mean, we can meet first time and hang out. I don't know.
Yeah, definitely.
Yeah. Good luck then.
Alejandro, you have a question?
Yes, thank you, Arash, and thank you so much, Spencer. Nice to meet you.
Yeah, you too.
Thank you so much for the presentation. Really nice, and also surprised with the really high laser powers you work with. And
Yeah, that's
so
good from big to small. That's the aspect I was trying to highlight. It's yeah, different regime.
Yes, I mean the most powerful laser power I use is the one I have. I mean, I work with in the lab that is 1 watt, but of course, you compare with terawatts. I mean, nothing related. But I would like to ask you more about this laser powers experience. Like, how is working with these high laser powers in terms of damage, in terms of security, and
yeah. So I mean, especially in Hamburg, when I was really in the laser lab, you know, I had my hands inside under the boxes, tuning mirrors, replacing cables, everything like that. I mean, your daily kind of routine for working is very different. You have to wear goggles. You have to pay very close attention to which ones they are. You also need to know where the beam path is in 3 dimensions because depending on which laser it is, it can burn you. We had some pump lasers that had 20 joules in them of infrared nanosecond light, which will burn you very severely. All types of things like that. And yeah, you need to know, let's say, a greater range of properties of any optic you're going to put inside. We had a lot of problems with damage where it turned out that one optic was being slightly damaged, not because of the electric field, but because of the heat that was going on it. And you know, it was a polarizer or a half wave plate where 2 sheets of glass were bonded to each other, and the heat was causing that bonding to deteriorate, and that was causing back reflections to come off of that, which were then damaging something else. So it's really kind of a system that is working under tighter specifications where you really have to care about everything. And there's always the kind of nervousness that comes along with how you have, you know, let's say your nonlinear crystal or your sample or whatever that you want to do an experiment with, that basically if its properties aren't what you think they are or what the manufacturer told you, maybe it'll get damaged and, you know, you're a little bit screwed there. But in the end, you know, you always go slow. When you're new, you don't go in there by yourself. It doesn't make sense. It's intimidating. You have someone else who knows what's going on, and you start slow. And you always say, should I do this experiment now, or should I test it at, you know, 1/10 of the power of the experiment and make sure everything's going well? So you have to just be more careful and slow.
Yeah, I asked this question because also when designing an optical system and even considering high laser powers, it becomes really hard to find a manufacturer or a provider for this kind of optics, for example.
A lot of times they won't even specify it for you because they don't want to be liable. They say you're buying this and it's your risk. And you know, there are also probably 10 different ways to measure laser damage threshold, and it might depend on wavelength, it might depend on pulse duration, it might depend on spot size. So basically they might give you a number, but then if you damage it, they'll just say that your regime didn't correspond to what they tested, so it doesn't matter anyway.
And in this kind of non-linearity effects, because for example, we have here also we have a femtosecond laser, and for 2-photon polymerization or 2-photon effects. And when I was designing the system, I found some challenges on finding the optics to keep the bandwidth, for example, of the laser. So in this experience, I mean, you find, for example, specific manufacturers, or how was this process, for example?
Yeah, well, we had the issue also that we had to buy a lot of large diameter optics. And in the end, there was a very, I might say something wrong, so don't think of the specifics, but it was the company CVI, which used to be Melgrio, but I think the ownership changed, whatever. They had I think they were producing optics on the Isle of Man. So in between the island of Ireland and England and Wales. And I believe that facility shut down, and then it was coming from a different facility, and the quality either went up by a lot or went down by a lot. I forget which one it was, but it was really the same product from the same manufacturer, but something was different about the clean room. So, the damage threshold changed by a factor of 2, which if you're being careful, then it's okay. But if you're near the threshold, then that factor of 2 really matters. So yeah, in the end, you need to know the man or woman to call on the phone and to tell you what's really going on and where stuff is really coming from and what can they really promise. Even if the price doesn't change, you just need to know. Yeah.
Okay. Thank you so much, Spencer, and welcome to B-Phot.
Yeah, thank you.
Thank you.
Thank you.
Such a great turnout, a lot of people interested.
Yeah, it is more people than I expected, actually, because I think the original survey you sent, there was like 12 attendees, but I guess that was just a representation of the eventual.
Yeah. Oh, well, those are the people voting for the time and day. But I also had a question, maybe while other people are thinking and coming up with more questions. I saw a part of the movie Tenet in your presentation, some part in the flying focus slide. The pulse was going back in time. What was happening there?
Yeah, exactly. That's what I tried to caution against, because I don't want to imply that I'm breaking causality. Let me I can share my screen again. You can see it.
Yeah.
So this flying focus is actually depending on 2 pretty simple parameters. So it's depending on this pulse front curvature. Sorry, So this pulse front curvature, you can think of it in 2 ways. It separates the pulse front in time from the phase front, but you can also think of it just as chromaticity of the lens. And what that means is the focal length of the lens depends on the wavelength. And that's just because the refractive index depends on the wavelength. So if you were to use the thick lens formula to calculate the focal length, it would have a wavelength dependent term. So if you look at the focus, it means that wavelength 1 is focusing here, wavelength 2 is here at the center, and wavelength 3 is here. So they have their best focus position at different positions around the ideal focus. And you can combine that with temporal chirp, which is just the different frequencies are arriving at a different time. And if you combine the different frequencies arriving at a different longitudinal position and a different frequencies arriving at different time, then you can actually control the arrival time and therefore the velocity of the intensity peak. And that's only true in this case around the focus, because only around the focus do you get a different intensity at different longitudinal positions, because the different colors are really focusing. So it actually is kind of like a transient phenomenon. It's only around, so you have your beam and you're focusing it. It's only occurring around the focus. So watch again, and at the end, you'll see as the beams defocus, all of a sudden again, they're all traveling at the same velocity. So it's a localized velocity that's different. So this one is traveling slower. The second one's traveling slower than the speed of light. And the third one's traveling backwards. But when they defocus again, you actually can't see it because of the color scale. But outside of the focus, if you were to be able to see with the color scale, they would all again be traveling at the speed of light. So that's why, and if you had a screen and you could magically measure the energy that was traveling through your screen, it would also be traveling at the speed of light. It just happens to be that at this position, the other colors are less focused.
Right.
So they don't make the intensity peak occur. So to be honest with you, it took me weeks or maybe months to understand it. So, you know, it's not, but the point is that it's not violating causality. The energy is still traveling at the speed of light. It's just that locally within the focus, the peak intensity is traveling at a different velocity than the speed of light. So you can make it travel faster than the speed of light, but it's not, you're not making energy travel faster than the speed of light or information, if you want to think about it from the information point of view.
Yeah, and does it have like a sort of application, or is it just in simulation? So, they haven't seen it experimentally.
Yeah, so this group in Rochester that published it, that kind of scooped us, let's say, in 2018. Yeah. They have a team working on it, and they have published a bunch of really interesting results after that, mostly with plasma physics. So they took a beam with these aberrations and focused it into a gas, and it ionized that gas. And the ionization front, they could also control with to have different velocities, because it basically just follows where the laser pulse is. Yeah. And I mean, they've also done other work, both experimental and theoretical. So it has some applications, but it's mostly in plasma physics, particle acceleration, kind of, also, let's say, extreme photonics.
Yeah. Thank you so much. Thank you. I think Rohan had a question. Do you, Rohan?
Yes. So,
perfect.
So I'm a master's student, and my question will be quite simple for you. But is the spatial temporal coupling only limited to highly nonlinear media and ultra short pulses, or?
Yeah, it is basically. The short answer is yes, and I'll show you kind of why. Just give me a second. So the short answer is yes, and why that has to do with you can see my slide?
Yes.
So the reason why it's limited to ultra short pulses is because I described it as the temporal properties varying with space. So this is kind of a cartoon of how it would look. But if you think about it from a frequency point of view, you know, here you have a certain pulse duration and here you have a different pulse duration. So also maybe the spectral bandwidth is varying with space. And in the other examples I showed, it was the direction of pointing of a given color or the convergence of a different color, you know, different colors focusing to different positions. So if you imagine you go to the other extreme where your laser beam has only one color, then that no longer matters. So if your laser beam is CW and you're going through a lens like this, the focal position will be shifted according to the properties of the lens, but it will still be only in one place because you have only one color. So basically, there is that aberration, but if you only have one color, it doesn't matter anymore. And you remember the analogy I gave between an ultra short pulse and looking at a scene with a camera. You care about that when you're looking at a scene because your scene in real life has multiple colors. But if you're working with a CW laser, you really only have one color. You know, that's why lasers are so important for a lot of applications. So it's really, and there are equations that can show how important spatial temporal couplings are, and they all basically become more significant, like the decrease in the intensity or the increase in the duration or something, they all become more significant as the pulse duration decreases. So the more ultra short your pulse is, the more likely these effects are to be important. So if you have a laser system that is 1 picosecond, you'll actually never care about this, even though that's still ultra short. It really needs to, basically the way to put it is that the bandwidth needs to start to become comparable to the central frequency, or the number of cycles within the pulse needs to become comparable to 1 or 10. So it really needs to be like ultra short, although I hesitate to, you know, add another term there.
And that basically like initiates a new question to me. If they are coupled, can we control like how much yeah, let's just say that let's just say we give a higher weightage to the spatial aspect and like transfer basically energy from spatial to the temporal, and can we do that?
Yeah, I mean, a way to kind of paraphrase your answer is, can you shape a beam spatio-temporally? And the answer is basically yes. I mean, in this case, with a lens, you're going from not having any spatial temporal couplings to having something afterwards. And actually, this Optics Express, I use a lens doublet that's made of two specific lenses to impart a specific value. So it was designed with really exotic glasses to impart a precise known value of pulsiform curvature. But you could also use that to shape the pulse. One way to do it is if you put it here, or if you put it here, like say you have a beam that's converging, if you put it at different positions while the beam is converging, it will shape it differently. So this is actually one topic that I'm kind of, let's say, interested about, is there's some expertise at B-Phot in freeform optics. There might be a connection between freeform optics that have dispersive qualities and spatial temporal shaping. So maybe that's, something cool to look into. Obviously, it's new because I just spoke about it for the first time, but that's a potential thing.
It seems very interesting.
Yeah.
Thank you.
So thank you so much, Spencer, for your great presentation.
Thank you, everybody, for the good
Story.
questions.
Yeah, and thank everybody for their questions. Amazing again. I would like to also welcome Yousef, our next presenter, to maybe say a few words about his presentation. He's going to be presenting for us in I think last week or the second to last week of March. And its title is going to be From Iran, a Digital Hologram. So if you could please, Yousef, say a few words.
Yeah, thank you, Arash. Actually, the inspiration of this presentation comes from an article in Physics Today years ago. As Spencer mentioned, that he had a little bit of a difficult time, proposals, rejection, stuff like that. Well, we scientists mostly don't talk about these stuff. We just come with our results, and we don't talk about the personal aspects. We talk about research, not the researcher. So I thought a lot about, if I want to talk about myself as a researcher and the experiences that I've gone through, which project that I did would be the best. And I thought, because it was a complete experience of everything that could happen, at least to me, I mean, the most complete experience, everything that could happen to me in my life, I decided to talk about my holography project. It's a 3-year project that I did back in Iran. I'm just going to mention it. There's not going to be a lot of data, and the basic physical concept of it is so simple that it's going to take, like 5 minutes to explain everything. But I'm mostly going to talk about my experience as a researcher back in Iran, especially as an engineer working with physicists. What would that mean? And I hope it's going to be interesting and fun.
Yeah, it will surely be very interesting. Thank you so much for being our next speaker. So everybody, is going to be also an open and public presentation. So I hope that you will have time to show up. This presentation, as well as the next one, will be recorded and shared in our YouTube channel and our social media. If everybody could please turn on your camera so that we can take a final picture and finish the meeting, I would be grateful. Will you do it, Ashley?
Yeah, sure.
Thank you.
Yes, if you can take out from the spotlight the user, sorry. Okay. Then we will be complete. Yeah, great. So please hold on. I will take like 2-3 pictures. One. More people are coming. Smile.
Great. Thank you.
Thanks.
Also, don't forget about our events. Like we have a photography event that you can actually submit your beautiful pictures to. And there is another one, logo contest, that you can actually make your mark with the B-Phot chapter and make a logo for us. Am I forgetting anything else, guys? If not, we can close the session. Thank you so much for turning up, and see you next time. Goodbye.
Bye-bye.